Okay, so good afternoon again, everyone. Welcome to APNIC eLearning web class. Now, today is Wednesday, the 7th of October in 2015. It's actually already 1 p.m. in the afternoon from Brisbane in Australia, where I'm broadcasting this class. So this is the second session out of 3 that we are going to cover for today. It will run for 1 hour, and the topic will focus on DNS security. So here, I would assume that you have some idea of, well, a lot of us obviously have an idea of what DNS is, how it works, and what is the basic function of DNS. And so in this session, we will be looking at the vulnerabilities that are included or you can find in a DNS hierarchy or DNS system. And how do we secure them? What do we do, or what does the standards show us that can be done when it comes to DNS to protect our systems? So we will be looking at those things. Prior to that, I just want to briefly introduce myself. My name is Cheryl Hermoso. I am part of the training team at APNIC. So as part of this team, we do conduct workshops and either face-to-face or e-learning like this to members of the internet community in the Asia Pacific region. So the topics that we do cover are catered for the internet community. So we do network security, IPv6, BGP, routing, DNS and DNSSEC, and internet resource management. Now for this session, this is provided for free to anyone who's interested. A lot to improve the service that we're already providing to everyone. So with that, I'd like to go through and start this this topic. So what are we going to look at in this session? First of all, there is an assumption that coming in this session that you kind of have an idea of what DNS is. But just very briefly, I'm going through a few things to introduce some terminologies and some basic functions of the DNS system. And the reason for this is I want us all to be on the same page so that we can all identify, we can all see what are the possible issues, what are the possible weaknesses and vulnerabilities that you can find in DNS. Okay, and then through that, I'll show you some examples of these weaknesses, some of the attacks that have been going on, where are these vulnerabilities, and of course, the more important thing is how do we now protect that? What are the different ways to add security for our DNS servers? There are two main things that we will be looking at. Now, we have a different session later on that discusses DNSSEC, but I will briefly introduce that in this session. So two main technologies that should be implemented with DNS are transaction signature TSIG and DNS security extensions or DNSSEC. So those are the main things that I want to cover for the next hour. As in every session that I do encourage participation from everyone. If you do have questions at any point in time, please just write them down on the chat panel. By the way, audio and video is not allowed from the participant side, and the reason for this is because we want to preserve bandwidth for those of us that are joining with limited connectivity. So for everyone's benefit, we will only allow, if you have questions or any suggestions or comments, please write them down on the chat rather than raising your hands. Okay, so with that, I'd like to just very briefly have an overview of the DNS and how it functions. What are the different parts of the DNS system? So now, to be able to understand that, of course, the main thing, the basic thing is when and where do we actually use DNS? And the answer to that is quite simple. We want to use DNS. It's kind of a third-party service, a third-party system that we want to use to, of course, find out some resources based on the resources that we have. So usually one resource is IP address, the other resource is domain name or vice versa. So if you have a typical question, if you have like going to a browser and wants to access www.apnic.net, what do? Or what does your machine do? Your machine will act as a resolver. Okay, so this is a resolver. A resolver basically is a basically it's a function, it's a utility that is part of your operating system that does check with a DNS server about these mappings. So from your resolver, it will try to communicate or contact a recursive name server such as this. Most recursive name servers are also caching name servers. Now, I'll show you why. The reason is because when you do a recursion, okay, a recursive DNS server does a recursive query until it finds the answer. So it goes like this. So you're asking for what is www.apnic's IP address, and so it goes through a hierarchy. It starts with the root. Okay, root server is at the very top of the DNS hierarchy tree, and then it asks that question, hey, what is the IP address of apnic.net? And then obviously, if you're familiar with DNS, there's such a thing as delegation. So most likely, root server has already delegated the nodes that are in it to other parties. So other people are responsible for that particular zone. So it doesn't know the answer. So what it does is to refer you to the next possible place that you can check. In this case, the top level domain. So it refers you, hey, go ask this IP address. This is the top level domain server, TLD server. You can ask a question. So recursive server does the same thing. It goes to the GTLD, asks the same question. GTLD most likely doesn't know the answer because, again, it has been delegated, right? And then so it does that same recursive process. That's why it's called a recursive server. It does a recursion from the root, going down the hierarchy tree until it reaches who will be able to give the answer. So in this case, that's your apnic server. It knows the IP address 192.168.5.10, and then it gives it back to the resolver. So from this diagram alone, you can see that DNS is a distributed system. It doesn't just like rely on itself. It's not a one machine operation, but it relies heavily on communications between this server, recursive server, and all the other servers around the world. Different DNS servers from root, GTLD, and all the others. Now, most recursive servers are also caching. The reason for that is because you have many clients connected to the same recursive name server. And so if I already have the answer to the IP address of apnic.net, I don't have to go do this recursive process over and over again. Okay, I already have that in the cache for a limited time. That time period is what we call as a TTL, or time to live. Okay, so if another machine, another client goes to that same name server, it will be able to get the answer in a faster time because it doesn't have to do the recursion again. So that's basically how DNS works. And you see that you are using a lot of servers. Just with this name server here, okay, that's what we call as the authoritative name server. So if there is a particular server that can answer for a particular zone, that is your authoritative server. And an authoritative server usually is not just one. You have at least two for redundancy. So we have a hierarchy called primaries and secondaries. So they have to share the information among them so that they can consistently answer for the same domain. Okay, so that's how DNS practically works. So the problem there is, so you know it's hierarchical, you know that there are many different parts to the DNS system, there are many different servers that are communicating, you have resolvers, you have cache, you have recursive servers, you have authoritative name servers. So where are the possible issues? Where are the possible vulnerabilities in DNS? So if you can't think like a hacker right at this point, can you tell where are the possible points of attack that you can do in a typical DNS system? So this is the same kind of similar diagram as the previous one, right? It just starts from here. This is your machine, your computer, your laptop, which is your resolver. This is your recursive name server. And this one is your authoritative name server. Okay, authoritative name server, you have primaries and or masters, and slaves, or what we also call as secondaries. So they're both authoritative for the zone. Inside your primary server, you edit zone files. Zone files are your actual records, resource records. The actual mapping that you wanted to know resides inside either a text file or a database, which is what we call as the zone file. Okay, so another one is like if you want to make changes into the zone file, this resides in your primary server and propagated to secondary name servers. Again, the reason for that is because they're both authoritative and should be able to answer for any queries for that zone. So zone file in the master will be propagated to zone files in your secondaries or slaves. If there are machines, let's say in your NOC team, you have say a zone administrator there, and he wants to be able to do dynamic updates to those zones, then usually there's also an option for that. Dynamic updates is when you want to make changes. Maybe you want to add, remove, delete, or edit a resource record, but you don't want to restart the service again. So it is done dynamically while the service is running. So having said all of that, where do you think are the possible vulnerabilities here? And the answer to that is, well, it's practically everywhere. Okay, it's practically everywhere. It can be within communications among the different servers or among the different machines, or it can also be the actual data or the actual resource records that resides inside your zone file. When you talk about communications between different servers, what could possibly happen? So here you have your master and slave set up. So your master, like zone files in your master, are propagated to your slaves. So what is the possible problem? Someone can impersonate the slaves, pretend to be slaves, and so get the copy of the zone file from the master. On the other way around, it can also be that, okay, you have your real slaves, but there is a master server that pretended to be that master, meaning by doing address spoofing, IP address spoofing, he can do that. He can pretend to be that master and then propagate wrong information or wrong zone files into the slaves. So impersonating of master can result in unauthorized servers communicating and exchanging incorrect data, incorrect resource record. You can also have machines that are pretending to be your, say maybe your authorized machine to do dynamic updates, and he can change anything in your master server, right? What else? Maybe you have here your cache, your recursive server goes to the master. Master can also be pretending and then forward wrong information to your cache, and therefore that will be propagated to your resolvers, right? So interactions, any form of communication between these servers here, can have an impact on the correctness of the data and the integrity of the servers that are communicating themselves. Another one is the data itself. How sure are you that the information or the resource record that you got from this are all correct? Maybe it's the wrong server, therefore the data that you got are not supposed to be the correct mapping. Okay, maybe there is a domain www.apnic.net, but instead of pointing to the correct name server, now it's pointing to a different machine. Okay, it may look exactly the same as your as the website, the original website, but actually it's not. And since you trust that, you put in your credentials, you put in your sensitive information, your username and passwords, and the next thing you know, someone else, an attacker, a malicious user, already have your information and can use it in bad ways. Right? What else can happen? The contents of your zone file, your resource records, are inside your master server, right? It can be corrupted. If someone is able to compromise this server, he can edit the zone file, maybe remove some, add some information in there. So those are the main things that can go wrong in a DNS system. And as you all know, DNS is a critical infrastructure. It's kind of easy to set up if it's just a small one, but it can easily scale. And it's a critical service because all of us, many applications, many people, many users, all rely on DNS for these mappings because we all remember names rather than numbers, right? So the two main things that you will be looking at when it comes to DNS vulnerabilities are problems or issues with the server, communications between the servers, and also the correctness of the data itself. So when you want to protect DNS, what do? You provide server protection, you provide data protection. So let's look at some ways on how this can be done. Now, before we actually go into that, so I keep telling you about these possible vulnerabilities, but does it actually happen in real life? The answer is yes. One of the popular types of attack that happened about 5 to 7 years ago was called DNS cache poisoning. This has been, on paper for the last 10, 20 years perhaps, but it's not actually, there's no actual attack, but it's only within the last 5 to 7 years that they noticed that, yes, actually, it can be done. What is DNS cache poisoning? So you already know how DNS works. Okay, it's something like that. Replies will come to you from the authoritative name server and given back to the client. Now, your DNS server here, okay, normally answers to many questions. Okay, you have many clients, hundreds of clients, or even thousands of clients. And so every question or every query that I send out will have a particular query ID. Now, before this query ID is incrementing. So if one client send a request, query ID is 64571. Another client send a request a few seconds from that, query ID will be 64572, then 64573, 74, and so on. That's how it works, right? So now how does that affect me? What if there is a malicious user, right? There's a malicious user, this one here, and he wants to pretend to be the authoritative server. This time, our authoritative server is this, ns.example.com, who can give this mapping. Okay, the IP address for example.com is 192.168.1.1. But there's this malicious user who wants to poison this cache. He wants the mapping to be incorrect, right? Maybe he's pointing to 192.168.1.100, right? So what does he do? Or 1.99 in this case. He will send a lot of replies. Those replies, hundreds or even thousands of them, will have varying query IDs, hoping that one of those query IDs will match. So when I send out this query with a query ID, if I receive an answer, I will match that with the query IDs that I have in queue before I send it to my client, right? So if one of that matches, let's say for example, that's 1.99, then that will then be forwarded to this client. So even if this one here replies, because you still do the same process, normally these types of attacks are targeted. So this guy here will be sitting quite closely, maybe 1 or 2 hops away from my cache. So the reply will come sooner or faster as opposed to the reply coming from here. So if I already received a reply and then I receive a reply from the correct name server, that second one will no longer be accepted because I already had the answer. I've forwarded that to client. The client is now accessing a website which is a false website, okay, a dodgy website, which is meant to get information from him. So that is DNS cache poisoning. The idea is to put incorrect information to this DNS cache so that clients that will connect to that will get that wrong mapping, wrong information. Now, what actually aids this is if you are also running what we call as an open resolver. I might have that in the next one, not yet. But when you say open resolver, this DNS server is open to everyone. It's public. You may say that we should be very careful, right? Only limit your DNS resolver or your caching server or your recursive server to limited people, maybe your clients, maybe your enterprise network, maybe to your customers, but not expose that to everyone else on the internet. Why? Because that can be used, it can aid in a lot of attacks. At the same time, it can make DNS cache poisoning quite easy. Why? Because say I don't know the query ID. This guy here, this malicious guy doesn't know the query ID. It's just like hoping that within the range that he sent, one of that will match, right? But if this is an open resolver, I can actually send the query to this server, and now I know what's the query ID. So I have a smaller range, and one of that obviously is bound to match. So it makes it easier to do cache poisoning in this sense. Another type of attack that has been very used in the past 2 or 3 years, is what we call as a DNS amplification. Amplification is an attack on different UDP protocols. The first one is with DNS. After that, the year after, they did it on NTP, they did it on SSDP, and a few others. But it started with DNS. What exactly is this? So you have a lot of bots, right? Robots, basically compromised machines. Maybe they were they were infected by a virus, a Trojan, or a malware, and stuff like that. And so they become compromised machines. There is an attacker, there's a command and control, and then we will send the same commands to all of these compromised machines. Now, all of them will be using spoofed IP address, and then they will send a query. It's basic, right? I will send a query, what is the IP address for www.example.com? And that query will go to the same process, find the authoritative name server. Now, since you're using a spoofed IP address, what will happen? The reply will it will not go back to these compromised machines. It will be redirected to a target machine. So let's just say this is your victim. So all the replies will be going to that victim. And one of the reasons why this is called amplification attack is because when you do a simple query, you can all try that. When you do a query, okay, you do a dig at localhost or dig at server IP address www.example.com, the question is actually just a few bytes, okay? But the reply is usually 5 to 10 times bigger. So it's much bigger, right? So the reply is amplified. So just think, if you have 100 of these compromised machines, the effect that it has on the victim machine is actually a lot. Okay, it's big, it's huge traffic that goes into this victim machine. And that is DNS amplification. Okay, so it's basically a reflection attack. So the reply doesn't go to the compromised machines, but to a victim server, and the replies are highly amplified. Okay, that has happened a lot over the past couple of years, so make sure that you have set up a few security measures to avoid being attacked like that. All right, so those are just two examples. I've also mentioned about open resolvers. If you go to openresolverproject.org, you will see there that there are still about 3 to 4 million open resolvers out there. And you don't want to be running open resolvers because it can be used in different forms of attack. Okay, you can aid, you can be an accomplice to a crime if you do that. But when you set up DNS, by default, I'm pretty sure this happens to most of the DNS applications. By default, it's open. It's an open resolver. So if you don't add access lists, if you don't limit the availability of that server to just a few networks, then you are actually acting as an open resolver. All right, so those are just some of the attacks. And as you know, the main thing there is, once someone has infiltrated or has affected your DNS settings, okay, they can influence the way that you access the internet, okay, can lead you, okay, into, say, websites, dodgy websites, and you'll still think that you're accessing your company website. Okay, so it's quite dangerous. So the question now here is, how do you secure your DNS? What measures can you do to provide that form of protection? Now in this slide, I just pointed a few things that you can do. Basically, a lot of them would rely on the application that you're using. Now, among the DNS applications out there, DNS Bind is the most popular, and it runs about, I don't know, 75 to 80% of the world's DNS servers. So some of the examples or some of the things that you find here are mostly for DNS Bind, but there should be an equivalent one for all your other DNS applications, right? So first of all, of course, you want to run the most recent versions of your DNS software. Okay, that's not always possible. Okay, maybe you have limitations, server limitations. Up until now, we see DNS servers that are running bind 4, 5, 6, 7, 8. Okay, bind 8. You shouldn't use bind 8 anymore. You should start using bind 9. Okay, because there's a lot of like vulnerabilities in older versions of bind. But up to now, we still see them. So if you can, if you're able to, make sure that you run the most recent version of your DNS software. If you cannot do that, for example, maybe you're running bind 9, but you're running bind 9.3 or 9.4, whereas we already have bind 9.8. So if you cannot update to the latest bind 9.8 for some restrictions, then just make sure that you have the latest patch and that patch has actually stabilized your system. Okay, no more loopholes, no zero-day vulnerabilities. Next one, this is what I've been telling you for the past 2 or 3 slides. Make sure to restrict your queries. Queries are questions coming from resolvers, coming from machines. So you limit who can access that. You can add ACLs or access lists to specify only, say, your local network. Or if it's public IP address, specify only the IP range that is assigned to your network. If you are a service provider, you provide this as a service to your customers, you allow that only to the IP range that you have given to your customers, or if they're using portable address, only the blocks that are assigned to them. Okay, but just make sure to restrict who can access, who can query from your server. Another one is to prevent any form of an authorized zone transfer. So what is zone transfer? We've talked about authoritative name servers. Masters, slaves, they're both authoritative for the zone, but you only make changes in the primary or the master server, right? And then it will be propagated to the slaves or the secondaries. Now that is what we call as a zone transfer. Once the data has been updated, it should be propagated, okay, and transferred to the slave servers. Now, you want to, of course, prevent any type of unauthorized transfers. Don't make sure to limit it only to the IP address of your slaves. Now, later on, we will find out a more secure way to do this. But at the very beginning, just make sure that you limit it to only the IP addresses of your slaves, no one else. Why? We all know that DNS is a public data, right? They can query for that, for those resource records, but you shouldn't allow just anyone out there to get a copy of your entire zone file. Why? Because you're exposing your system, your network, your topology, because of all those mappings. You give them an idea of what services are deployed out there, okay, in your network, even if they're maybe it's only available locally or stuff like that. Okay, so make sure to prevent any unauthorized zone transfers because of that reason. Another one, if you're running bind, you want to run it with least privilege. We have something called chroot. So most implementations, they do that. So it's kind of you're jailing the service to run in a smaller vacuum that is part of your operating system. So if it is somehow compromised, then it doesn't affect the rest of your system. Okay, only that part. It's only isolated in that part. Another one, randomized source ports for obvious reasons. Secure the box. Okay, you can only be secure as, of course, the box that runs that service. So make sure to add firewalls, make sure that your operating systems are updated, make sure that the latest patch has been applied, make sure that no one has access to, say, some valuable ports or SSH ports, telnet ports in that server. Okay, and then the last one here is if you're running DNS, you should have this. You should have tsig, you should have DNSSEC. So these two, I would say, technologies answers our main problem. So if you have time, go back through 3 slides from here. That slide that shows the different DNS vulnerabilities. And notice that the 2 main problems that we have is either one, concerned with the server, and the next one is concerned with the data itself, the resource records. So if you implement tsig or transaction signature, it addresses the server issue. If you implement DNSSEC, it addresses the data protection conundrum or issue. Any questions so far? We're still okay? All right, so now let's look at those two technologies. First of all, let's discuss a little bit about TSIG, or transaction signature. So if you can see there, transaction signature is all about making sure that you're connecting, you're exchanging data with correct servers. So which servers are we talking about here? The primary servers and the secondary server. Okay, primary name server connecting to the secondary name server, or secondary server pulling the primary name server to get the most updated version of the zone file. So TSIG is actually a way of protecting the exchange of those messages between the primary and your secondary, and vice versa. So you're providing integrity here, okay? You're providing secure communications of queries and responses between your primary and secondary. But how do we achieve that? So before, in the previous slide, I told you that you want to limit who can, do zone transfers. So it actually addresses the same thing here. But the problem with the first solution before, to add access lists with IP addresses, is that IP addresses can be spoofed. It's easier to spoof IP address. So if someone, maybe you've put up restrictions. Okay, I'm a primary server. I can only allow zone transfer to IP address 10.0.0.1 and 10.0.0.2. So those are my two secondary name servers. So I only allow that to do zone transfer or get the zone file from me. Now, if there is an attacker, and then that attacker will configure his server to use 10.0.0.1, then the transaction is still a success because he's using a spoofed IP address. He stole the IP address so that he can be trusted. Now, with transaction signature, we're trying to prevent that problem with IP address spoofing, by instead not relying on IP address, but we will be creating what we call as a shared secret key. So here comes crypto. So it can generate a shared secret. It can be a password. It can be basically you have an option. It can be just a single passphrase, or you can generate one from the utilities provided by your DNS software. So that's your shared secret. That shared secret has to be sent. Maybe you generated it from the primary. That has to be sent to the secondary. And so every transaction that happens between them, they will check that particular key. So this is how it works, right? TSIG kind of protects any of those transactions, unauthorized updates, impersonating masters and slave, any form of pollution, basically anything that has to do with exchange of data between servers. And how does it do that? Then you first must configure your master to use a key, right? And then you share that key to the slave. The slave will also then configure his server to use that key. So notice, slave has this key, master has the same key. So when I want to do zone transfer, so that's usually query dig AXFR. AXFR is zone transfer. So this slave will go to the master, request for a zone transfer, and the master will reply with the content or copy of that zone. But before that process happens, there has to be a check. So slave, when it does the query, it will attach the key on the request itself. The master will receive it. Master will then verify that the key in the request or the question is the same as the key that he has on himself before he replies, before he responds. So here, he was able to verify that the signatures are both correct. It matches. So he replies back. So that's one way. Now, of course, when the slave receives the response, he also has to check whether the signatures is a match, right? Why? Because it's not only one way. Master checking or verifying the slave. It should also be the same, that the slave does not just trust any response that comes to him. He has to check with the master whether the reply actually came from the master. And he can do that by verifying that the key that he has configured in himself is the same as the key in the response that it got from the master server. So that's how TSIG works. It's not just between masters and slaves. It can be within one client going to any of these servers when you're doing dynamic updates and all that. Okay, but essentially the idea there is you will have a key. That key will be shared between the parties that are communicating with each other, so you have that form of verification, right? And so how do you now do that? Now, these examples here are the steps being done if you are running DNSBind. So these are the steps that you have to remember. First of all, you have to generate that secret key, right? You do that on your primary name server, and then you will share that later on. There's a utility in DNSBind called DNSSec keygen. Okay, that is a utility that you use to generate keys. So here, you just need to specify that the algorithm is a symmetric key algorithm, so it will give you one key, okay, that shared key. And then you provide the number of bits, maybe it's 128, 248 bits, it's all up to you, and then minus n host, and then the name of the key that you are going to use. Make it as descriptive as possible, because in one DNS server, usually it will have many slaves for different domains, for different zones, so it can become confusing very easily. So just make sure that the name of your key is as descriptive as possible. Now, once you have generated that key, you have to, of course, transfer that key to the secondary name server or any server that will, of course, communicate with your primary name server. Make sure that that is done in a very secure way, right? Make sure it's done in a secure way. Maybe SSH, maybe SCP, maybe you do it by yourself, etc. like that, okay? And then after that, of course, you configure both the primary and secondary servers and then test it. Let's look at that. Let's look at the configuration. So you've done the generation, the DNSSec keygen, you've done the communication of that secret key going to the others. Now check whether, okay, the configuration, this is what they call as named.conf. So check named.conf, okay, and add some information in there. Add some configuration in there. It should look something like this. It seems like some of you are having issues with bandwidth, and this is not as smooth as they wanted. So we will be uploading the videos later on if we can. Okay, if not, there are already available ones in our YouTube channel that you can try to play if you cannot follow the live session. So that's one thing that you can do. But hopefully that gets fixed from your end. Anyway, going back to this, so configuration, this is how it looks like. This one is your primary, this one is your secondary. In your primary server, you specify the key. Well, this one, key and server statements are all generated by DNSSec keygen. So it's essentially just adding that onto your configuration. So two main important things. You have key statement and server statement. In your key statement, you provide what algorithm was used to generate the key and the actual shared secret. Okay? And then you specify a server. This server statement tells the IP address of the secondary name server. It can be one, it can be a few, but essentially what you're saying there is for server 10.33.50.35, any transaction between myself and that server, we will use this particular key, which is this name, which is the key that you have previously identified. Okay, and so now this is your zone statement. Basically, that is the that statement specifies what domains or what zones you are authoritative with. Before, you'll have an option saying allow transfer only to this IP address. Now, since we're now using keys, you change that. Instead of an IP address, you'll add allow transfer only to servers that are using this key. Okay, so that's what you do there. That is the configuration. It's just a few lines, right, added onto your primary server in its named.conf. And then in the secondary server, it's kind of the same. Key statement, server statement. And then you have there, you don't really change much in the zone statement there. It's still the IP address of the master. But essentially, after you've done this, any communication that will be between them will look for that secret and then check whether they are the same. Okay, now once you have finished with that, then try to do it. try to test whether you can still do a zone transfer. So we said that you only want to do zone transfers between servers that are basically you have configured to be your masters and slave, right? So you can do it both ways. Like you can try it from your actual primary and secondary servers, or you can also try it in a different server without the key. If it's coming from a different server without the key, then the transfer should fail. If it's coming from your secondary server, that zone transfer should be a success if you have configured it properly. Okay? If you have provided the wrong key, obviously it will result in a transfer failed error. Now, one thing to remember with TSIG, okay, and this is very important, TSIG is time sensitive. So between your primary and the secondary servers, make sure that there is no significant time difference between them. Otherwise, the transfer will not occur. Okay, so those are the things that you can do. Configure TSIG. It's actually quite simple, and the concept behind it is also simple. It's basically you want to use keys which will be shared between them rather than IP addresses that are easily spoofed. Any questions? Okay, I'll go through DNSSEC very quickly because later we will do a session that is purely about DNSSEC. But my goal here is to introduce you on this topic and relate that to the DNS vulnerabilities. So far, we have looked at TSIG and how it can protect transactions. So basically, server protection. Now, the other one is data. So our scenario is like with the cache pollution problem, right? Actually, those incidents about cache pollution actually triggered, okay, the massive or basically massive adoption, I guess, of DNSSEC. And the reason for that is if someone was able to pollute your cache, how sure are you that the resource record, that the data that you're getting from the DNS servers are all correct? Do we have a way of checking? If I tell you that the IP address for training.apnic.net is this IP, would you believe me? And is there a way to check that? Right now with the current DNS system, there isn't, right? It's kind of trustful in a way. You have some form of checking. You have that hierarchical recursive query. But after that, once you have the information, once it is on your server or on the client, there is no way to check. Okay, is this actually the real one? How do you check whether it's a real one, right? You're doing integrity check. You use signature. Okay, you want to make sure that this has been signed by someone and there is a way to verify that signature. So if you think about cryptography, crypto, right? Now you're looking at using public key crypto or asymmetric key cryptography to do this. Why? Because you can generate keys. Two sets of keys. One is private, one is public. And you know how that works with asymmetric cryptography, right? You use that, you use one to sign or to encrypt, and then you use the other to decrypt or to verify. Here we will be using that for verification purposes. Okay, your sender, okay, or your server will sign that with its private key, expose the public key out there, publish it out there so that anyone that can receive or can get queries later on, get answers later on about resource records can verify using that public key that it is correct. Okay, everybody got that? We're using public key cryptography to verify the authenticity of the data that you got by using the public key to verify the signature. So we will achieve that by using DNSSEC. So as its name implies, it's basically DNS security extensions. There are a few RFCs that is used for that, RFC 4033, 4034, and so on. But the idea basically is to protect the integrity of your data by verifying the digital signature and establishing what we call as a chain of trust. What is chain of trust? So we know that the DNS hierarchy starts with root. So root delegates it to the top level domain delegates it downstream to the second level, third level, and so on. So you have there a chain, right? And so by using fingerprints of your public key, you can establish a chain of trust. Okay, so with this one, if you are going to implement DNSSEC, it guarantees a few things for you: authenticity of your data, integrity, that the data actually comes from the right source, from the right server, and another one is the non-existence of a domain. You will be able to verify all of these things. All right, so how does DNS work? Basically, it's the steps here. You have records, resource records. These resource records are inside your zone file, right? And then you can sign them. Records are signed using a private key to prove its authenticity and its integrity. Okay, now the signatures itself are published. Okay, after you've signed it, the output is your signature. It has to be published. So when someone does a query, it still gets the typical answer. Say, I want to find out the IP address of training.apnic.net. So I send the query out. So it still gives me the answer. The A record will point to this IP. At the same time, I can also get a signature of that record. Okay, because that signature is published, I can have two, and a record for my query, and then a signature of that record that I just got. Okay, next one, public key. If I'm the server that signed this, I use my private key to sign it. And then later on, I will also publish my public key so that these signatures that clients were able to get can be validated. They can do an integrity check and verify that yes, this is actually signed by that authoritative name server. Okay, everybody can follow that. And the next one, child zones will sign their records as per usual using their own private keys. So every level, if you're authoritative for a zone, you can generate your public and private key pair and sign the zones that are assigned to you. But to establish chain of trust, the parent zone will sign the hash of a child zone's public key to prove that chain of trust that we are talking about. Okay, parent zone signs the hash of the child zone's public key. It's quite a lot to digest actually, because DNSSEC is actually quite complicated concept. Okay, but by looking at these steps, it should give you a very good idea of how it can be implemented. It's all about integrity check. It's all about signing your records and then publishing those records, okay? And then publishing your public key to verify those records. At the same time, we're establishing what we call as a chain of trust, okay? By signing the child zone's public key, basically a signature of that public key, and then adding it to the parent zone. So you're achieving that kind of trust and integrity that the data that you got is actually correct. All right, do we have any questions? So these are the vulnerabilities protected by DNSSEC, basically the data that you got from the typical query and also cache impersonation. Okay, I will skip this. I assume most of you will be attending the next session later on, but there's still quite a few things here about the resource records, basically about the implementation itself. Now you know the concept on how or what DNSSEC is for. Now, how do you implement them? First of all, there are new resource records that are introduced to achieve the goal. You want to be able to publish that public key, right? You must have a container for that. Okay? You want to be able to publish the public key as well. You should have a resource record that addresses that. So those resource records are RRSIG, DNS key, DS record, and NSEC and NSEC3. If you're familiar with DNS, you know that the different resource record types that are typically used are A record, quad A record, CNAME, PTR, NS record, SOA records, and all that. But here we are adding, or we are introducing a few more. Is there a way to mitigate DDoS attacks to a DNS server? It depends on what types of attack is happening. If it's towards a DNS server, I mean the DNS application itself, which is an application layer attack, then you can do that by restricting access. One is, I've told you about it, limit again access by doing ACLs. Another is, if you're familiar with DNS amplification, I talked to you about it earlier, then you can do rate limiting. Okay, limit how many queries are allowed from particular networks or particular IP addresses that you are receiving at any point in time. So that's what we call as rate limiting, and that is a way to mitigate DDoS attacks or DNS amplification attack. So look it up. Depending on your DNS application, it should give you the structure on how that can be implemented. So for Bind, that is doable. For NSD, that is also doable. Okay, so I'll probably end there. I'll discuss more about these things in the next session, which is pretty much the DNSSEC discussion. But what about testing? How do you know if you're getting signatures, right? How do you verify? You should have a validating DNS resolver. Okay, your validating DNS resolver will tell you whether the answer is an authenticated data. So when you do a simple dig, it's dig, the typical same commands, but dig plus DNSSEC. And then this is an example you can see there. You requested for a pointer record for an IP address, and then you got an answer. You got your pointer record. At the same time, you also got the signature, RRSIG, for that pointer record. Okay, that's the signature for that record. And that's how you verify it. All right, so do we have any other questions from the chat? Anything that you guys want to clarify? You can write them down now while I'm giving you the link to both the survey. Actually, the survey is there. If you want to look that up, if you cannot access that, it should be this one. Let me just grab that link for you. So please take a bit of time to do this survey. And then the slides, you can download them from our FTP page, okay, which has all the PDF materials for today's sessions. That's the link over there. You can see it. So if there are more questions, please type it in the chat. But otherwise, I think that's pretty much it for me. Thank you very much for your time and for your attention. And you know that if you have any questions later on, you can always send us an email at training@apnic.net or contact our help desk team. That's helpdesk@apnic.net, or you can contact them through different other means. All right. I don't see any activity from the chat right now, so I think that's pretty much it for us. Thank you very much again, and I hope to see you in the next e-learning session. Bye-bye.